Hello, welcome again everybody to another edition of online GES 103, I guess the COVID-19 edition. So this week we are going to be talking about Chapter 2, Matter and Minerals. Prior to the semester, this is the section that I am always excited about. I love getting to talk about minerals and rocks. My daughter, my 5-year-old, is well, she's a hoarder. She hoards everything, but rocks especially is one. Every time we go for a walk, she takes everybody's rocks out of their driveway, makes me carry them in my pocket home, and now I have buckets and buckets of rocks, roughly 3 years worth of collected rocks in the driveway that she will not let me throw away. But she's super interested in it. It's something that she and I look at all the time and go like gem mining, cute things like that. So something that I really enjoy, and unfortunately we don't get to really go about the same way that I had intended at the beginning of the semester, so that's kind of a bummer. Anyway, so we'll do what we could do. I apologize, last time a few times I forgot to remove my image. So if anybody catches that, please let me know, and I'll send you the notes that I forgot to uncover, but we'll try. Okay, so anyway, so I guess week 2 of this, we're working on rocks and minerals today. But first, of course, so in my previous classes, I'd always include a weekly comic or something. I haven't done much of it this semester because of I get sucked into looking at these because to me they're hilarious. I have a really kind of dry sense of humor, and this one had me on the floor rolling. This was one of my favorite ones I've seen. So to me this is funny. So those of us that grew up in the 80s, which is none of you, and 90s playing video games like Asteroid, obviously the double meaning here, asteroids making dinosaurs go extinct, ha ha ha. My wife, who's incredibly smart and definitely much smarter than I am, she and I had very different sense of humors, and so jokes like this she doesn't get, so I laugh when I explained it to her. She basically rolled her eyes and then walked away. So hopefully one of you found it funny. She certainly did not. All right, moving on. All right, so chapter 2. So these are the 3 sections that we're dealing with, 2.1, 2.4, 2.5. With 2.5, I think I even parted down further in the lecture, which you'll see. So use what I talk about in the slides that I give you in 2.5 to reference with the book. There are pieces that the problem with this section doing it online is it's hard to do it without having a visual. At least that's my experience of how I learned it and have taught it in the past. So the visual helps this section a lot. We don't have it, so I actually cut out tons, right? So we're not going to cover in chapter 2 the chemical composition pieces, so the chemistry. So you're welcome, everybody, because I'm sure it would have been challenging for some, if not most, given it's probably been a few years that you guys have touched chemistry, and doing it on your own might have proved some sort of consternation, so I got rid of it, didn't want to deal with it. But with that, I kind of avoided kind of more complex pieces within this chapter. They're incredibly important, but I don't honestly know how to do it through YouTube video in a way that's going to make sense and fair to everybody. So again, you're welcome. I don't think anybody's going to complain about that. So with that 2.5, it's not the entire section, so when we get there, I'll probably forget to mention it, but just reference what I talk about or what the slides show, and that's what I want you to know specifically to 2.5. With 2.1, 2.4, you're responsible for the entire section, okay? Just let me know if that doesn't make sense. All right. So, talking about rocks and minerals. Frequently, we refer to absolutely everything as a rock. I assume most of you haven't had much experience dealing with the peculiarities of minerals. And I don't mean like they're particularly peculiar, but they have their own definitions, but we generally, colloquially speaking, we call everything a rock. So the question is, are rocks and minerals the same thing, or are they different? And as you should assume, because I'm asking this question, they're indeed different, right? They're not the same. And that's what we're really going to dive into, not as deep as we would have if we were sitting in class. But by the end of this, you should have a pretty good understanding of the difference, and then the definitions and kind of characteristics behind them, right? So broadly, right, minerals and rocks are different in that rocks are really kind of compositions that are aggregates of minerals, right? And a mineral is kind of its own thing, right? Big definition, but let's get into more of the nuance. All right, I'm going to try to remember to move my picture here. All right, so a lot happening on this page. So what we're looking at are general properties of minerals. So the chapter in the book really talks about 90% of the time talks about minerals. We talk about rocks kind of loosely. So that's what we're going to do. We're going to focus on the minerals being the most important piece of this this unit. So the key concept is, or the differences are, that minerals are simply the building blocks of rocks, right? So that's the difference. And that's basically what I said, was blocks are essentially aggregates of compositions of different minerals. So for millennia, humans, in one form or another, I guess, have been using minerals for all types of kind of utilitarian purposes, and they have their own economic values. So, very early on, flint, chert, right, we've been using as weaponry. So like your arrowheads, think of that, early spears, early tools. Quartz has a big economic component, right? So, big example of that is quartz it's got a lot of silicon, and so we use it for a computer chip, right? Salts, obviously use it in a lot of different applications. In my world, it just makes everything taste really good. I love food, I love to cook, and I use salt in everything. Yes, salt is a mineral. It comes from a mineral called halotite. A lot of people probably don't know that, but if you lick a block of halotite, it tastes like salt. So therefore, that's where your salt is coming from. And then a lot of your native elements, your gold, silvers, and coppers, right? And so those obvious applications, jewelry, coppers, your copper wiring, right? And so what the book tries to impress upon you early in the chapter is basically everything that is manufactured in some way contains minerals. Now, that's not entirely true, but it's largely true, right? And so you come into contact with minerals on certainly a daily basis, and mostly every minute of your day, like even in makeup, right? You have talc in makeup, and that certainly is a mineral. So the question, and I actually remember to move that, is every industry, and this kind of goes back to like we call everything a rock. Well, there's also kind of confusing definitions to what a mineral is, right? And so we have this colloquial ways in which we use this, like your health industry, right? We always hear about, the benefits of vitamins and minerals in terms of your diet or health, right? And I guess that goes also with the bottom bullet point there with food. But then you also have, the mining industry uses the word mineral to basically describe anything they extract from the ground, right? And so it's one of those kind of overused terms, but in kind of geological perspective, there is a very precise definition to it, right? And so that's my question there at the bottom. How are we going to define what a mineral is? And so the book provides this definition. There's some, it's pretty consistent with other definitions I've seen, so we're just going to go with it. So for your exam and understanding of the chapter, this is the definition I want you to use. Basically, any naturally occurring inorganic solid that possesses an orderly crystalline structure and a definite chemical composition that allows for some variation, right? And so I understand that's kind of a big definition, but it has within it, you can break it apart. We have these 5 different characteristics that can be found to identify what a mineral is and what a mineral is not. If a mineral does not, it can have, let's say it can have, 4 of these characteristics, and I'll move my image here, but missing one of them, right? So let's say we're trying to identify what a mineral is, and we're saying, yeah, it's naturally occurring, it's inorganic, it's solid, right? It has a definite chemical composition, but the structure of the atoms aren't orderly, right? What I mean by that, they're not repetitive. They're kind of random in nature. That what we're trying to identify by definition then is not a mineral, right? And I think that makes sense to most, right? So you have to have, it has to align with these 5 different characteristics, right? So it's got to be naturally occurring. It's got to be inorganic. I put generally because there is some examples out there, I guess, that do or can possess, but that's not what we're going to talk about. It kind of goes beyond the scope of this, especially the way that we're doing this now and things that I've cut out. So inorganic, we'll just go with that, right? It's a solid substance. So the example here would be like ice, right? Ice is a mineral, right? And I think I mentioned ice later in the lecture or my presentation, but water is not, right? And if we think about ice, ice not in your freezer, but like ice in, let's just say, the Arctic, right? So naturally occurring ice is natural. It's certainly inorganic. It's solid, right? It has a crystalline structure. So under magnification, you can see the repetitive crystalline aspect of it, and it certainly has a definite chemical composition, right? 2 hydrogens, 1 oxygen. I have a note here, and this isn't specific to ice, but all minerals right here at the bottom, the definite chemical composition. There is allowed some level of variation, but it's very precise, I guess, and is defined. So that's kind of the important piece. So there is some variation allowed, but we know exactly what it is. So substitutions of elements, you do see, but again, that kind of goes beyond the scope of what we're going to talk about. All right, so what we're going to do is talk about each of these 5 individually. Mainly because they're the most important piece of this chapter, right? So they're pretty quick, so kind of bear with me. I try to provide a couple examples that you can see, because the cool part of doing the mineral section is they really cool pictures. My daughter, I talk about her all the time just in general, I talk about her all the time because she's, rad. I take her to the rock lab at school, or used to, and she would spend hours going through each of these drawers. And obviously, she doesn't care anything other than they're shiny and pretty, but I try to teach her these things. But, it relates to these presentations that they lend themselves to be interesting because they're visually alluring, I guess. All right, so first characteristic of all minerals, they are naturally occurring. There's over 4,000 known minerals, known and named, I guess, minerals. Not all of which are natural, right? So we have man-made. And so the examples I give here, and you don't need to know these are actually man-made. There's plenty of examples. Most of the rest of the examples I give in the presentation are all natural. So I thought these are kind of cool. These are ones I don't even, well, I know what carborundum is and obsidian. I didn't know what this titanium flame is, so I looked it up. It's kind of neat. So anyway, so this example of the carborundum, this is a naturally occurring mineral. However, it's not that it's scarce, but it's kind of hard to mine in any great volume, and it's also really tiny. But we all know what carborundum is because it's used in applications where like grit and abrasive ability is needed, like sandpaper, right? That's what carborundum is used for, but because we need a lot of it, most of this is produced in factory for commercial use. Blue obsidian, I've never seen a blue obsidian. This is one of those examples where obsidian is certainly naturally occurring, but it's volcanic glass, and I think we've all seen that, especially with like arrowheads, perhaps. Like if you recall back, maybe you did like field trips in elementary, middle school, or something, or maybe you have some at home. I don't know, right? But we've seen these these really dark, black, glassy rocks. That's obsidian, right? And that's volcanic glass. Basically, you have these volcanic extrusions, and the lava cools so quickly that it can't develop any real crystalline structure, right? And so it's not a mineral, but we know what it is. But in this particular case, blue. That's the problem with blue obsidian, is that blue is not a naturally occurring color for obsidian, right? So these are things that are treated and made within a laboratory. And then this last one, this is a good example because we see things like this a lot. We have this particular one as a titanium flame aura quartz cluster, right? So whatever that means, a lot of words, right? And so they basically took these quartz crystals and they adhered gold or something. In this particular case, it is gold, but they basically can adhere some sort of metallic element to the outside to give it these really cool shades and colors, and yeah, it's just decorative pieces, right? Anyways, I found these interesting because, well, again, minerals and rocks are cool, so I spend a lot of time looking at them, but you don't need to know these for the exam, so sorry to waste 3 minutes of your life on that. All right, moving on. We have, so minerals are formed by inorganic processes, right? And so a mineral basically can't be made of anything that at one point was alive, right? So that rules out coal, right? Because what is coal? You know, coal, I put the little, here, let me move this. I mean, everybody knows what coal is, right? But, you know, it's formed from, you know, vegetation, from plant life. So in this example, right, you had what's called prehistoric vegetation being buried underneath these swamp, dirt, water over a period of time due to pressure. It's turned then into coal. And that's why it burns, right? We use coal for, you know, when I grill tonight, I'm doing salmon steaks tonight, coated in wasabi mayonnaise, which is going to be delicious. Anyways, but I use a particular type of coal that you can use for your grill. But it burns because it's plant life, right? I'm not trying to burn a piece of granite. So it's all organic. So yeah, so basically, again, minerals, whatever it's made of, it couldn't have been alive at some point, right? And again, there is a couple kind of exceptions to that, but very minimal, not enough to worry about in this class. All right. All right, so minerals are solid substances. And I have here water, no, ice, yes, right? Let me move this. All right, so ice, and this is what I referred to before, kind of jumped the gun, I apologize. It's naturally occurring. It's an inorganic solid. It has a definite chemical composition, yes, 2 hydrogens, 1 oxygen, and it has an ordered crystalline internal structure, basically being the atomic arrangement repeats over and over and over and over. So we know how to define it based upon this arrangement, right? And I did put a note here, and I said it before, I believe, it's only naturally occurring ice, not what you're doing in your freezer, because it's had man-made influences, right? I guess I should probably just leave this off for a second. All right, so the orderly crystalline structures. And so this is really the key element, I think, at least. I mean, I somewhat argue, but this is a key element to me of what you need to understand of what makes a mineral, right? So the atoms, the atomic arrangement, these the ways in which atoms are bonded are done so in a predictive manner, right? And so they're orderly, right? And they repeat. And because you have this predictive element of it, we can look at a particular sample when we're trying to identify it. And if you looked at it at that level, right, that subatomic level, you could identify it based upon this this arrangement. But what this arrangement gives you is what we generally, you know, a word that's probably overused when we're talking about minerals, but it gives you the crystals found within the minerals. And it goes back to like why obsidian is not a mineral, and the cooling process of the lava basically occurred too quickly that it couldn't form these crystals, right? And the crystals are essentially a byproduct of the orderly arrangement, right? And so this particular image, you don't need to know the geometries here. I apologize, I keep looking back because my dog is about to do something and make a lot of noise, so I'm trying to he generally is well behaved, but you know, it's a dog, So I've tried to ignore him until he barks and scares everybody. Okay, so anyways, so with this, it gives us particular growths. So if you look at the orderly arrangements of these, you look at these kind of drawings, this is how they particularly, or the particular way in which they grow, right? They all have that unique quality, but also when we go into like how they break, meaning if we were to smack a mineral, a lot of them we know how, but they're going to break along lines of weak bonding, and maybe that may not make sense now, but this bonding, the atoms, the way in which they bond, some bond stronger than others, and they're always going to break along these weak lines or these weak bonds, right? And it's going to give us these different shapes. So anyways, long way to say they have orderly, repetitive, crystalline structures, okay? All right. Another definite chemical composition, which allows for some variation, right? And so the analogy for this is just like baking. You don't really need to know what goes into a pancake here, but basically every mineral has its own chemical composition, right? Makes sense. What makes granite different from quartz is what's what's in that mineral, and it doesn't change, right? So any sample of quartz, of granite, of an emerald, whatever it may be, is consistent from sample to sample. Again, yes, there is variation, but it's very minute, and so it's not. Again, in this class, don't worry about it as much. The book kind of talks about it in some terms, but just know it's generally it's consistent from sample to sample. All right. I think that's it. Yeah. Okay. So the example here at the bottom, we have 2 salt, sodium chloride, right? NaCl. Again, you probably know chemical composition of salt. You certainly don't know quartz. They talk about it in the sections that we're skipping in regard to chemical composition. Not a big deal. Here the example of quartz, silicon dioxide, SiO2 is not the same as SiO3, right? So if it has an extra oxygen atom, it's not quartz, right? Meaning the O3 instead of the O2. All right. Hopefully that makes sense. I think everybody gets it intuitively. All right. So then that's a mineral. So what's a rock? So like minerals, naturally occurring solid, but it's a mass of mineral or mineral-like matter. Easy enough, right? And I've mentioned a couple of times, so essentially just an aggregate. It's this combination of different minerals, right? It also can have non-mineral matter, right? It doesn't really matter. Sorry, I made myself laugh. So you can have kind of an agglomeration of minerals, but then you can have, some non-organic, some organic piece of something, whatever it may be. Let's say this is mixed with coal somehow, mixed in with it. Well, it's still a rock, right? So the biggest difference is it can just be a combination of things, right? Towards a mineral is its own, unit, right? It's repetitive. We know exactly what it is based upon its, its crystalline structure. So when we talk about the aggregates, the most important thing here, so you're aggregating the minerals together, so different whatever they may be, but within this process, these minerals are maintaining their own individual uniqueness, right? Nothing really changes. Now, it can, certainly within, the environment of, deep within the earth with, heat, pressure, or, some sort of chemical reaction, they can certainly change. But when we're looking at these rocks, what makes the mineral, if it's still a mineral or identified as a mineral within the rock, it is a mineral, right? All right. So these rocks, the terms in which we use, we identify them simply by the composition, so what's in these, but then also the texture. So we're talking about like the grains within it. You know, is it smooth? Is it rough? Are the grains big? Are they small? Right? And so this is a piece of granite, this example here. I think I have another one. I don't remember, maybe it's the next slide or slide after. But if we were to zoom into all these particles, and this is granite's a really cool one. You know, everybody uses granite for their countertops, or at least had been. It's kind of moving towards quartz now. A little home ownership there for you. So I have granite countertops. Many of you probably do at home. They're really pretty because they're full of different minerals, which give different colors, different levels of kind of reflectivity. But they're made up of, you know, again, just a bunch of stuff, right? So hornblende, that's your mica. I know this is really tiny. So these are your micas. There's two different kinds of micas, your quartz, and then your feldspars, right? So this is kind of this is generally what quartz always is. Really pretty. You get all these different colors. Let me see. I think I got everything. Oh, okay. So the non-mineral matter, right? So rocks can have like your obsidian or your pumice. So we talked about obsidian, again, comes from volcanoes. Pumice is the same, right? It's lava, basically, which cools really rapidly, but it's also very gaseous, has a lot of kind of gas rising through it, but it cools so fast that you have these big vesicles, these big holes within the pumice rock itself. Pumice, probably, as you know, has household applications like see, my wife uses it to, she's not here, so she can't hear me. She uses it to like grind down like the calluses on her feet, which is kind of gross to me, right? So she sits in there and rubs calluses and dry skin off of her heels. She's a runner, so she gets calluses that she doesn't want, right? And so again, household application, yes, to me that is funny. Others, not so much. And then also coal, which we've talked about. All right. All right, so general kind of outline of this, right? We but minerals kind of as a standalone component. We have different categories of how different categories of rock based upon the ways in which they're formed, right? So your igneous, your sedimentary, and metamorphic. Igneous are, you know, they're formed via you know, let's say lava, right? Have we talked about this in class? I don't think we have yet. Sedimentary is just a composition of layering process of different rocks being essentially smushed together, or minerals, I guess I should say, over time. And then your metamorphic, in which minerals, rocks undergo a particular type of change over a period of time, right? From these, we then can have individual rocks within each category. Right, so hopefully that kind of made sense. So within each of these three categories, we then have, because these are the ways in which they were formed, right? We have then your gneisses, sandstones, or granites. And there's plenty more, right? But they're all going to fit within one of these three defined categories. Example, again, yeah, this is maybe a better example of what I did before. This is your granite, right? So we have pieces of quartz, your hornblende here, and then your feldspars, right? And so again, you look at these under magnification, and then you can see things like, and we'll talk about it here in a little bit, these your different forms of cleavage where they were, I'm not gonna say fractured, but they were broken, right? And they all kind of maintain their similar properties, but this is what we talked about. This is a smart figure. You can type this in from your book. So if you don't quite get it, these videos, I keep saying it, are really good. I don't think many people watch them. Please do. They do a really good, kind of quick and concise way to explain these. All right, so properties of minerals. So these, we're talking about the properties being what we look at when we're trying to identify a particular sample, right? And so we have diagnostic properties, but we also have like these ambiguous properties. So when we talk about your diagnostic properties, these are the ones that, absent anything else, these are going to hold true within a specific sample of mineral. I know that probably didn't make a whole lot of sense, but these 5 different ones, your optical properties, your crystal shapes, mineral strengths, densities, and then there's kind of a category of other. If you have a sample of let's say, I don't know, quartz, all of these kind of subcomponents to each of these 5 will hold true regardless of the sample. Right now, again, slight variation. I get it. That's kind of confusing. Nobody likes kind of these open-ended ideas, but you know, it is what it is. Whereas we then have these ambiguous properties. And so unfortunately, when we're trying to identify these, and these are what we all do, students do, we initially look at a sample and we look at the color. And we use the color as a way to try to identify what the mineral is. The problem is many of your specimens, the colors can greatly change, right? So like a really good example that, you know, my daughter and I find all the time is like quartz, right? You have like a smoky quartz, which is this kind of dark charcoaly color. You have, what is it called? Like I want to call it creamy, but that's not right. Cloudy quartz, I think, is what it's called. Towards it's really, you know, it's opaque. And then you have like a rose quartz, which is pink, right? So if you're using color as the only guide in which to identify what a mineral is, like you're just not going to be able to do it with much precision. Now, it is useful, right? And so though you're not doing your labs, if you have your lab manual, you know, there's a chart in the lab book which basically is kind of a step-by-step process towards identifying a mineral. And so you look at some general characteristics, and that's what these diagnostic properties are. And you're basically going line by line, and you're kind of answering a set of questions, and by the end of it, you're coming to a decision of what these samples are. All right, and this is where obviously doing this in class would be a heck of a lot more interesting than me talking about it, but you know, everybody needs a grade, right? So this is what we got to do. All right. So optical properties, there are 4 of them. So in this slide, we got 2. So we talk about luster. Luster is simply, it's the appearance, excuse me, of light reflected off the material or the mineral, right, the sample. So with these, we have metallic and we have non-metallic. And I think these are pretty self-explanatory. This here, this galena is metallic. These others are non-metallic. And really the explanation for why one is shiny, let's call it, versus the other is the presence of some sort of metal, so like iron, right? So galena has got a lot of iron, so therefore it's shiny. These non-metallic ones do not, right? And so with these, we have different, your non-metallics, we have different ways in which we refer to them as vitreous, glassy, and dull, right? Within your metallics, you also have a submetallic, and submetallic simply means I can have a sample of galena, right? In this example, it's shiny, but I can also have a sample where it's very dull, and it's simply because it's a function of kind of oxidation, I guess, right? So copper is another one of those where this sample of galena was recently broken, so someone struck it, broke it in half, so the inside hasn't been exposed to air. And so it still has that very reflective metallic property. Once you kind of get that oxidation process, it's going to really dull down. And that's what we're referring to as submetallic, right? It doesn't change the fact that it's still galena and it's still this particular mineral. It's just the actual appearance. So remember, think of these in terms of what we're doing to go through the process to identify what this sample is, right? So if I hand you you know, this piece of graphite, and I say, and you don't know what it is, right? But I hand you the sample and say, figure out what this is. You know, the first thing that you would maybe do is look at these optical properties, and you would identify first off that is certainly not a metallic in appearance, right? Graphite, for the you probably know, right? Your lead pencils is not lead, you know, it's graphite. And if you have a sample of graphite, if you hold it, it feels very slick. It's very greasy. It's kind of weird feeling. I know some people and students in the past, they don't like holding it because it just feels odd. I think it's kind of cool, but it does feel, it feels like you want to put it down and your hand would be covered in something slimy, but it's not. All right, so metallic, non-metallic, subcategory there is submetallic. Again, same thing, it's just been oxidized. Color, right? We just said color is not a diagnostic property. You can certainly use it, especially when you're looking at the charts in your lab manual. I'm not honestly sure what you guys are doing for lab now online. Maybe you're still doing this, but you can use it again as kind of an aid. You know, if all else fails, you know, start finding the colors to these things. But it again, colors can change from specimen to specimen. Is all I can say. All right. More optical properties, two more. Streak. Many of you, and I'll move my picture here in a second. Many of you may remember back to maybe in high school. It's been a long time for me, but maybe in high school you guys did like streak plates, where you're simply taking a specimen and you're grinding it across a piece of unglazed porcelain. And all you're trying to do is get the mineral or specimen, whatever it may be, in powdered form. Right, the powder form of the mineral is its true color, right? Because you got to think it's kind of like that galena example where you have the oxidation, so you can be looking at the specimen as a whole and it not really be its true color. But if you're grinding it on a plate, you're getting some of that, some of the mineral that hadn't been exposed to oxygen yet, and so you get you can identify the color better. So if you look at some of these examples. Maybe this limonite is the best, where the streak here, it's a lighter shade. I know this is kind of a blurry picture. Lighter shade than the specimen as a whole, right? All right, so just think of these as your true color. Here's a question to think about, and this is for you maybe more specifically in the lab. We have 5 samples here, but only 3 have an actual streak, and it's not, so they took these minerals, right, so your amphibole and then your pyroxene, they rubbed it on the streak plate, but there's nothing. Does anybody know why? Right, I think you can kind of intuitively figure it out, but we'll talk about this a little bit later perhaps. Maybe I should leave that for the question of the week. No, because the book doesn't talk about it. Okay, no, it won't be a question of the week, but see if you can think about that for a second. Why do these, the pyroxene and amphibole, not have a streak, whereas these 3 do? All right, easy enough, right? All right, the last optical property, ability to transmit light. Simply how translucent or opaque is the specimen, right? So if your specimen is opaque, light's not getting through. Think about it like you're basically going to take a specimen, hold a flashlight underneath it. My daughter and I do this all the time because frequently by doing that you're illuminating things in the mineral that you wouldn't see otherwise, and you can have some really kind of pretty characteristics. So anyway, so something that's opaque, right? Nothing, no light's going through if you're shining a flashlight on it. Something's translucent, some light is going through, but you can't essentially transmit an image. And all I mean by that, if I were to hold the specimen up to like a printed word, you can't read the word through the image, right? So it's getting translucent, but it's not transparent, which is the last one. So if a specimen is transparent, both light and an image are able to be seen through it, right? Simple enough, yes, hopefully. All right, so that was the last optical. Your crystal shape or habit, these are cool. Yes, this mineral here does exist. We have these in the lab. Those are really neat. Okay, and I kind of touched on this earlier in the lecture, that your crystal shape, also referred to as your habit. I just refer to it as crystal shape because I think that everybody understands what that means. It's essentially just the characteristic shape of the particular mineral, of the crystals within it. Because remember, they grow in a particular form because of their repetitive crystalline structure. So they're always kind of going to grow in some sort of characteristic way. So you can look at these shapes and use it to identify then what the mineral is, right? If you have minerals that are just kind of all over the place, that can grow wherever they want, that makes it really hard. But because we know that they kind of grow in a kind of a uniform way all the time, that actually really helps. Now, again, variation, yes, but it's good enough as a diagnostic property. All right, crystal growth. So this is dimension aspects of it, in that crystals, they can kind of grow Some grow equally in all three dimensions, right? So out this way, and out this way, right? Some elongate in one direction, right? So if we look at the example of B here, this bladed, obviously, well, you can't see the picture, but it grew, if you see my mouse, right, the core of it will be back this way, and it kind of grew out, right? So it's one dimension. If you compress a mineral, so if it's compressed underground, right, it's being squished, well, minerals can grow out this way. So it might respond to being compressed in one direction or the other, right? So with this, let me move my picture here, cubics. So the book has a bunch of different terms for this, right? So I put equine, basically things are growing equally all the way around, right? Bladed, fibrous, tabular, cubic. Just know a couple of these. So the book has a list. I don't have it in front of me. Probably about 7 or 8, right? And so I might come up with a question on the exam of something specific to the habit or a crystal shape and say, you know, this is a term for shape, yes or no, something like that, right? So yes or no, so just kind of be familiar with what those are. At minimum, know where it's at in the book, as always, okay? All right, mineral strength. Pardon me. Again, another diagnostic property, which includes kind of 5 subcomponents to it. So mineral strength is simply how easy these minerals are going to break or deform, but it's determined by the strength of the chemical bonds, right, between the atoms. So to kind of define these terms that we use are hardness, right, and we're going to talk about these individually so I can show you pictures to make it a little bit easier, but hardness obviously is just, well, maybe not obvious, I apologize. But hardness is the ability to resist scratching or abrasion, right? And that goes back to the streak plate thing. We'll talk about that. I'll give you the answer to that in a second. Cleavage is the tendency to break along planes of weak bonding. Fracture is when it breaks, but in like a random pattern, right? It's kind of unpredictable how it would break when we smash it. Tenacity, see, there's my dog. Hey, go. He's getting ready to bark. Resistance to cutting, breaking, bending, and deformation. I have a Bart Simpson illustration for that. Hopefully you guys know who the Simpsons are. I am pretty old. And then also the specific gravity, which is the density. And I actually think I left that one out now that I think about it. But specific gravity being how dense is the rock. The book doesn't really talk about it. I think it gives you like half of a paragraph for it, so I probably left it out for that reason. So I apologize, just know that is a diagnostic property. All right, mineral strength, hardness. So hardness, ability to resist scratching or abrasion. To test this, we have a scale, it's called the Mohs hardness scale. So what we do, so again, remember the whole point of this is trying to identify what a mineral is. So we have 10 index minerals, right? So if you look at the image here, we know, or we've scaled these generally from softest is a 1, that's talc, talcum powder, right? Everybody knows what talc is, that goes in makeup and stuff like that. All the way to 10, diamond being the hardest, right? And so this is just ordered, right? 1 through 10. It's not saying that gypsum being a 2 is twice as hard as talc, right? Hopefully that makes sense. It's just an order. It's not some sort of like exponential function here, right? So it's just a way to easily kind of identify these. So anyways, the scale allows us to assign some sort of value, numerical value of hardness. So we know what these kind of index values are, right? Diamond 10, talc 1, orthoclase 6, apatite 5. But we also know the hardness of some general tools which we may use to test a mineral, right? So if we take our fingernail and we scratch, and we're actually physically able to scratch a sample, so we know a fingernail has a Mohs hardness of 2.5. If we can scratch a mineral, we know that it is something softer than 2.5. So if we're looking at a chart where we're identifying these, in this particular case, well, something softer than a fingernail is going to be like gypsum or talc. Now, I'm not saying that's what it is, but this is what you're going to be doing to kind of further narrow down these to identify what the actual mineral may be. Okay, so we have a steel nail, right? That's a 6.5, somewhere in between quartz and orthoclase here. So if a nail can scratch it, then we know when we're looking at these charts that that example, this sample is going to fall somewhere below it, right? But what if it doesn't scratch it? So let's say we're trying to take a steel nail, we're trying to scratch the sample, but it's not scratching, right? And all that really means is that, well, the mineral is harder than the nail. It's harder than a 6.5. So when we're looking at these charts, we would look above the scale number, right? And so we would look at anything above 6.5, or at least these categories, and then use the other diagnostic properties to identify it, right? All right, cleavage. So this is, again, part of your strength. So we talk about, you know, the bonding, the atomic bonding. Generally, they're going to bond, and there's going to be a weak spot. Let's just call it a weak spot. So one plane is going, or maybe more, one or more, let's say, is going to be weaker than the other. So whenever you break a mineral, it's going to have a tendency to break along a particular plane, you know, 1, 2, 3, 4, 5, however many directions. But with that, it's also going to maintain, it's going to break at particular angles, right? And this is kind of confusing in the lab when you're actually looking at a sample and I'm saying, okay, look at this sample and let's just use this hornblende here at the top. And we know if we're looking at this under, you know, magnification, that along the top and the right hand side here, when we smash it, it's going to break on these kind of two-dimensional planes. And then the angle of these two planes is going to be roughly 120 degrees, right? And this example says not at a 90-degree angle. Okay, so basically it's about 120 degrees. You know, these are not easy to see in this particular, but if we, yeah, here we go. Let's go over here to the feldspar. You know, you might say, well, why is it only 2 faces instead of 3? Because this looks like, this is called like a smooth plane, right? Maybe I should have started with fracture now that I think about it. But we're saying, or at least this example here is saying that this is a fracture, not a cleavage. So if you look at this closer, it's not smooth. There's a lot of irregularities to it. So the feldspar is a better example that this face, right, this too broke on a two-dimensional plane here at the top, right-hand side. In this particular example, the angle is 90 degrees, right? We can look at this and tell it's a 90-degree angle. And that's a good tell that this is probably going to be some sort of feldspar. But in this face here, you can see how it's irregular, right? We have this additional kind of plane happening here. It didn't happen very smoothly. Hard to tell in the pictures, granted, I give you that. Let me move my thing here before I forget. Okay, so then you have examples like your micas. This is muscovite. You also have like a biotite, right? And we all, you know, you've probably seen micas. I remember growing up, I would, you know, dig micas out of the ground, and you can basically take them and peel them away like sheets of paper. So the bonding is incredibly weak, kind of in a linear form, right? So you can literally peel it because the bond is really strong across the face, meaning you can bend mica. You can take a sheet of it and bend it and let go, and it'll snap back to what it is. But you can peel it apart like Post-it notes, right? And so that's going to show you where the weak bond is. So we describe your cleavages, and I have down here, by the numbers of cleaves, and then the angles, right? So the 120 degree angle in this particular case, there's a 1 and 2 cleaves, 1 and 2, 90 degrees, and then mica is like 1, right? It literally just peels. That's 1. But it could be a lot more than that. And this is where it gets really challenging in the laboratory environment when you're looking at a sample, you know, and especially you're not trained to do it. I have a lot of problems with this, but you're looking at it under magnification, and there's just, you can have a little tiny sample or even a big sample, you know, and trying to find what a cleave actually is, like these smooth surfaces, but that smooth surface can be fairly small. And you don't really know how this sample was treated, like where did, you know, it probably broke 100 times before it actually made it to the laboratory, right? So it's pretty challenging. Again, I find that to be probably the hardest part, the diagnostic piece, when you're taking the lab. Now, I don't know what you guys are doing, but I doubt they're saying go out and collect some samples. So anyways, yeah, so cleavage. In this case here, you have 3 faces, 1, 2, 3, 3, and 4. So it can be a lot and challenging, but important piece. All right, then the fracture. So as differently than cleavage, where basically you have these these smooth breaks, right? I'm going to take a sample, I'm going to smack it with our hammer. It's going to break, it's going to create a smooth surface. Well, as a cleavage. Well, then the other side is I can take a mineral and smash it. Now, this is a different kind of mineral, mind you, but it's going to fracture. And all the fracture is you have these irregularities. There's no real kind of symmetry to the break, I guess, maybe is a way to describe it. All right, so minerals have chemical bonds that are all equally strong in all directions because, remember our cleavage, we're saying that you have these weak bonds at different planes. That's why they break at a consistent angle and a consistent way from specimen to specimen. Minerals that will fracture basically have equally strong bondings all the way around. So when you break it, this is going to be a mess, right? And the easiest example of this is the irregular fracture here, right? So it produces uneven surfaces. That's this blue example. Let me move my picture. If you look at this, under magnification, even under magnification, you're not going to find any real consistency of the break. So it just, again, it's irregular. There's no pattern to it. This volcanic glass here, right? You have conchoidal fractures. That's that word, conchoidal. You've probably seen kind of things that look like this, maybe like in broken glass, like Coke bottles. So you don't have Coke bottles anymore. But you'd have kind of these circular breaks, right? So those are kind of cool. All right, your splintery fractures. Looks like little splinters, hence splintery fractures. And then your fibrous fractures. I showed you an example of this earlier. Yes, this is a mineral. It's really cool. Again, we have these in the lab. Nobody go to it. You're not allowed. I can't even get in the building anymore. They took away my access last week. I've been trying to go twice a week because it's impossible to work from home with 2 screaming kids. So my mother-in-law tries to help out the kids, and I've been trying to go to my office to work, to give my wife space, who also needs to work, but it can't go anymore. Anyways, all right. That's my complaint of the day, I guess. All right, tenacity. This is my Bart Simpson. Hopefully you guys know who the Simpsons are. Illustration. Makes me chuckle. Reminds me of my childhood. All right, so tenacity, simply how a mineral responds to the stress applied. Is it, in this particular example, is it going to bend? Is it going to shatter? Is it going to hold strong, right? So resistance to cutting, breaking, bending, or deformation. Basically, you're changing the shape, right? Let me move my picture here. So with this, we have 4 different examples. Your non-metallic minerals, right? We showed that. We know what non-metallic is. These are your quartzes. And I do want you to know, I gave you examples here. Some of these are in your, well, these are all in your book. I think the book even offers a couple more. I want you to know an example of these, okay? So write this down, have it handy. Because we can't physically touch these in class, I just want you to know what they are. Just give me the name of an example. I know you can't readily identify it if I handed you a mineral, say, what is this? But I got to kind of show it somehow. All right. Anyways, so your non-metallic minerals, these tend to be very brittle, and they'll break or fracture when struck by something hard. They're brittle because they don't have metals in them. If we think about what our uses of metals are, and this goes to the next thing with your native metals, metals tend to be very malleable. Like think of like copper wiring. So you can hammer it or stretch it, into particular form, like a wire or like a steel plate. But because it's lacking these metals, it doesn't have that malleability, so it'll just shatter, right? Your native metals. These are your golds, your coppers, your silvers. These are like your jewelry things, right? Not just jewelry, right? With a lot of other usage like gold, right? So spark plugs use gold in your car, if you guys don't know what a spark plug is. But these are very malleable. That's why they're as useful as they are, because you can shape them when heat is applied. Right, so that would be this example here, right? The cannonball hitting the gold plate. All right, sectile, that's your gypsums and your talc. So if you can basically slice it with a knife, you can cut it into different, pieces. It won't break, but it's not, you can't bend. I mean, it will break if you smack it, but you could something that you can cut and it'll maintain its shape, right? If you took like a non-metallic mineral here and try to cut it, it would break, right? It would basically just turn to powder as you're doing this. So if your gypsums and your talcs, right, these are, think of, if you know gypsum in drywall, right, you can cut through it and it's still going to maintain its kind of form. Now, it's mixed with other stuff, granted, and also has paper on it, which helps it maintain form, but that's kind of the point. So anyways, you can't bend it, but you can cut it into slices. Your micas, this was the example I talked about before. You can take a piece of mica and literally bend it in half, and it'll bend back to shape. All right. Put my picture back. All right, some different examples. Again, this is a smart figure. Oh, this is image I already used. Okay, so I kept this in here to show you there is a smart figure. So again, this is kind of a challenging concept. I would watch this one. If you're not gonna watch any, please maybe do one, and that would help. All right, other properties. So these are, so these are ones that are likely specific to a sample, right? So something like taste. Why would we taste a mineral, you may ask? And in the lab, I tell students not to do it, but everybody wants to do it because you have the mineral halotite, which is salt. And so everybody goes in there and licks it. And that's incredibly disgusting. Yeah, when I first came, and I would work with Dr. Royal. For those of you who know him, he's our rock guy. He's brilliant on a lot of different levels. But we would go through every sample together week after week. He would teach me so that I may spread the knowledge wealth. But he would want me to taste it, and I said, no, that's gross, because these samples have been there forever, and a lot of students are licking them. Disgusting. Okay, anyways, all right, so taste, your smell, like your sulfurs, right? I remember as a kid going to museums or whatever it may be, and they'd have stinky sulfur smells. They smell like rotten eggs. For those of you who have been to like Yellowstone, so I've been a few times, there's certain parts of it when you're around the geysers. Yellowstone's on top of a volcano, right? A lot of sulfur. So a lot of sulfurous fumes, and it's really stinky in certain parts. Kind of cool. So anyways, okay, so things like double refraction, you hold mineral on top of a word, it reflects it twice. You have like two words. Reflects the wrong word, refracts it. Anyways, magnesium is a feel, blah, 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 blah. Feel would be like the example of graphite. Remember I said it's like really greasy. You put it down, you expect your hand to be coated in something nasty, and it's not. And then your reaction with hydrochloric acid. All right, so now this is the last section. We're going to talk about mineral groups. So there's two types of mineral groups, your silicates and your non-silicates. So again, I think I said earlier, there's over 4,000 minerals. So, which is good that most of your minerals are mostly 8 elements, right? So that makes it easy. Because there's a lot of other ones. So generally within at least your first few kind of geology courses, you're really kind of focusing on minerals which are comprised primarily of these 8 or 12 when we kind of start throwing in some of the other ones. But anyways, so these we refer to as your rock forming minerals. Most of the Earth's crust are minerals that are made of these, primarily made of these elements. That's why they're called rock forming. I'm gonna guess, I don't even know what the book says. It's something like 90% of the Earth's crust, I'm gonna go with that, are made of these rock forming minerals. Okay, so your oxygen silicones, which if we look at the chart, right, and you can best believe this is going to be a question on the exam because there was a very similar kind of illustration when we were talking about the atmosphere, and we talked about main composition of the atmosphere. I showed you a pie chart, and then I asked the question in the exam of what are the two primary components of the atmosphere, and most people got it wrong, even though I gave you a pie chart. So this is going to be a question. Write it down. Please try to remember it. Oxygen and silicone. Okay. All right. So anyways, then varying amounts of aluminum, iron, calcium, sodium, potassium, and magnesium. So rock forming, there's also, the book talks about, and I think I mentioned later in the, a little bit later in the lecture, you have your economic ones. And so these are going to be your minerals that contain, and they can certainly contain pieces of these, but they're made of other different elements, and they're kind of found in scarce volumes, I guess. But they're really important economically. And I think I talk about some of these. So things like cement, right? So things that we put in cement are like ore. Okay, anyways. Okay, so within these we have, or not within these, but the minerals are basically divided into your different two mineral groups, your silicates and your non-silicates. They are exactly as they sound. Silicates are ones which contain silicon. Non-silicates do not contain silicon. So most of them, your main ones, right? So your rock forming, most of them do contain, while the others do not. All right. So here's our silicates. So this is by far the most common of the mineral groups. I think the book gives some sort of percentage to, I guess, the percentage of minerals which are, I don't know, it's high, 98%, I'm gonna guess. I don't know, not gonna ask on the test. So anyway, so your silicate minerals, they all contain your silicon, oxygen, tetrahedron. So basically it's your four, if we think of a tetrahedron, right, it's your triangles, 3 triangles, 1, 2, 3, connected together. At each point is an oxygen, and then surrounding a silicon in the middle. Oh wait, I have that there. There we go. 4 oxygen atoms surrounded a much smaller silicon atom. There we go. And I have a picture, I think, in the next slide, what the tetrahedron is. But that's important, right? So the tetrahedron is the commonality, and then they're basically chained together, being joined by different elements. And that's what's going to make the different minerals, right? So it always starts with this silicon, oxygen, tetrahedron, but they're bonded in different chains or planes or different clusters. Let me move this. By different elements, and these different elements, that's what's going to give it different characteristics to be a pyroxene or quartz or olivine or feldspar or your micas, right? There we go. So then arranged into groups based upon how these tetrahedra are bonded, right? That's what I'm referring to. Let me move this. So within your silicate minerals, there are also 2 different groups, and these are based upon the chemical compositions. And this is where I had mentioned earlier, I'm kind of eliminating some things I had planned to talk about because I think it could be challenging, and it's going to be challenging for some. So we're not going to talk about a whole lot of the chemical composition pieces. Just know the 2 different groups, your light silicates and your dark silicates. All right, light silicates. They're lighter in appearance. These are really, I said Barney style before, I think, in this class, right? It's Barney style. They're light in appearance, right? Their colors are generally lighter, and they're lower in their specific gravity. They're not as dense. So we could think of light meaning 2 things: light color, light in weight, density, right? And that's simply because they don't have, and I'll jump ahead a second, but your dark silicates have a lot of iron, right? So the iron gives it, and magnesium, but the iron gives it this dark appearance and also this higher specific gravity, right? So dark silica is darker in appearance and high specific gravity. Light silicates lighter in color and specific gravity. But what it does, it contains a lot of your aluminum, potassium, and calcium, right? And so that's why it's not dense, low specific gravity, okay? Examples of your light silicates, these are the most common. Your feldspars, nearly 51% of all your silicates are feldspars, right? It's a really common mineral. And then also quartz, right? Second most abundant. I didn't include a percentage there, not that important. Just know feldspar and quartz are your two most prevalent. But then you also have your mica. So there's two different types of mica. You have a muscovite and a biotite. In this particular case, we're only referring to the muscovite mica. So take a note of that, because in the chart in the book, and I think I have it coming up, there's two different kinds, and you'll see it in your book too, and they do differentiate. All right, anyway, so clay minerals, we know a clay. Okay, so back over now to your dark silicates. So this is your muscovite mica example. This example, and I'm going to move this real quick, for your dark silicates, this is a garnet. I love garnets. Whenever we do rock mining with my daughter, I always find all the garnets. Don't know why I like them. Dark red, kind of purple color, but they're really cool. They're heavy, they're small, but they're really dense. They're pretty cool. So my daughter finds them and gives them to me, so I collect the garnets. All right, anyways, so your darker silicates, most importantly with these, so this is what the mantle and your oceanic crust is mostly made up of, right? So these are olivines, your pyroxenes, and your amphiboles. I think I mentioned these generally earlier. Again, just know the examples, please. You don't really have to know what they are. The book breaks them down a little bit, but again, kind of hard to do without actually showing you what they are. I don't, because I don't want to go into the chemical structure of these to make this a little bit easier for everybody. All right, so different examples. Know these, know your lights and darks. All right, this is your tetrahedra, right? So they're kind of the condensed and expanded view. So again, there's your silicates, right? And so they contain a silicone atom. So we'll look at the kind of the expanded view. Let me move this. Yeah, you get it. Okay. So your 4 oxygens surrounding silicone, right? It's basically the 3 triangle faces. Then you have the base, the tetrahedra. This is what they all look like, at least at its most basic level. And then, let me move this. This is what defines them, right? And so you're taking a single, like up here in this example of the olivines, a single tetrahedra, but then you start kind of combining them in different chains and formations, including other elements. So you can look at the chemical compositions and see magnesium, iron, and then your silicate, your silicon and oxygen, right? They all end with the SiO2. What did I say, 2? Weird, 4. I don't know why I said that. Anyways, and you can see the different arrangement, the crystalline arrangement here. And then, if we really got into the chemical component, you can look at then, the cleavage, like where are these bonds the strongest, where are they the weakest, and this tells us, if you're looking at this level, how they would either fracture or cleave, right? This is also a smart figure. Feel free to type it in, from your book. It gives you the address, and it'll explain a lot of this if you need additional assistance. All right. And I promise you we're almost done. We got like 4 more slides. And most of these are just examples. All right, so feldspars, because remember, feldspar, the most important, are quantified 51% of your feldspar. So know these 2 examples, please. All you gotta know is the names. I just need you to know, some names of minerals. So we have potassium feldspar, and then plagioclase feldspar. Weird word, plagioclase. Plagioclase. Kind of a fun word to say. Don't worry about the sub pieces here. The book talks about these, but again, that's going kind of beyond where I want to go doing this YouTube style, right? So just know these 2, potassium and plagioclase feldspar. Quartz, second most abundant. This is what I talked about before. This is the example I was using. Milky. I guess I was wrong. The example I was using why we don't use color as a diagnostic or primary diagnostic piece, though you certainly can use it because Quartz comes in all different colors. Your Smokies rose, your amethyst is a form of quartz, and then your milky quartz, right? Milky quartz is what we see in driveways. That's what my daughter likes to collect. And of course, I have about 20 pounds of amethyst in a bucket somewhere. And yeah, anyways. So, second most common mineral. So again, know that feldspar and quartz, that's really what you need to know, are the two most abundant found in the Earth's crust. All right, two more slides. Some dark silicates, that's your garnet, right? And if you looked at this compared to the last image, it's definitely a little more translucent here, but most garnets are like that. If you hold a light up to it, it'll shine through. It's this really cool kind of dark red purple color, right? You have your olivines, your augites, and your hornblends. Our hornblends are kind of green, black green. Those are kind of pretty. They have really cool crystal structures when you look at them in the lab. All right, and then lastly, your non-silicates, right? So only 8% of the Earth's crust, that's what they represent, right? And I kind of mentioned that earlier. Silicates are the majority. I think I guessed at some number. I think it said 90%, so 92%. Yeah, that's pretty good. That's close. So most importantly, it's a non-silicate. It does not contain silicone. You best believe on the exam I'm going to ask some sort of question regarding what does or what does not contain a silicone and what that means. All right, so just know that's a non-silicate. Makes sense. All right, so with these, though there's not a lot of it, they have a lot of economic value, right? So again, that's your cement and your iron ores, right? Think about cement. I mean, cement's absolutely everywhere. Like there's a global shortage of cement because countries like, China are developing at such a fast rate. They're, using all the, the world's supply, right? So high economic value. So your carbonates, your halides, oxides, sulfides, sulfates, and then your native elements, which are your golds, coppers, graphite, sulfurs, and silvers, right? So again, just know these examples. You don't have to know anything about them, right? So what I would do if I were you is I would go through all the examples that I gave you in this lecture and create like a little Excel, sheet of just listing these by what they are, right? So silicates, non-silicates, just go kind of slide by slide. If I gave you an example, just write it out. That way it'd be a quick reference when you do take the exam. And if you want more referencing for these, it's certainly there in the book. All right, and last slide. Let me see if I got to move this. So these are your economic minerals. If you notice chemical composition, there's no silicone in these, right? You can go line by line if you want and look at the different economic uses. To me, this is really interesting, right? Because I think it highlights the fact that on a day-by-day basis, most everything we touch and deal with has minerals in it, and that's really important, right? Our food, our personal grooming products, your makeups, right? Most everything has minerals. So we generally think of minerals, especially when we're in a science class, and we think of these in scientific terms and these things that we'll never come across, they're just sitting in the yard or somewhere I'm going to dig up, but we use them for everything. And that's kind of the cool piece about these. It's more than just kind of looking at them, touching them, but understanding them, and then, ways in which we can use these to, our advantage, right? Okay, that is it. It took 1 hour and 13 minutes. I apologize. I was aiming for an hour. So I hope everybody's well, and I will see you guys five days for our get together on Wednesday. All right, take care. Bye.